So we'll discuss about the magnetic circuit. To start, do your thought that there are no secrets to success. The people who are successful, right? They need to work hard. They have to prepare well and learn from failure, right? So there is no secret. So this is the magnetic circuit in which you can see a source, and we are doing an analogy. For example, you can take on left hand side a transformers type of circuit in which there is a source to produce magnetic flux, and the flux is passing through the core, right? The circuit on the right hand side is an example of the rotating device motor we are using in our day-to-day life, and motor used in our home appliances. So it consists of stator. This part is your stator, and in between you have a rotor which is rotating in the air gap. So all this is example of magnetic circuit. So magnetic circuit is very important whenever, as we have seen in the last lecture, whenever we are using electrical machines to convert electrical energy to mechanical energy or mechanical energy to electrical energy, in between magnetic circuit link, right? We convert electrical energy to mechanical energy, right? Suppose you are converting this electrical energy to mechanical energy using motor, the example given here. Then in that case, the principle is whenever current carrying conductor is placed in a magnetic field. So the magnetic field, the magnetic circuit which we are using in motors or generators, when you are doing the reverse thing, mechanical to electrical, magnetic circuit is very important intermediate, right? So that's why when you study any concept of machine, જ્યારે પણ machine ભણવાનું હોય એની પહેલા you need to study the concept of magnetic circuits, right? આ clear છે બધાને? Any doubt here? Anyone? Any query to ask, huh? So magnetic circuit, you can tell, is a closed path which is followed by a lines of magnetic flux. So it is one kind of low opposition path to the magnetic flux where the lines of flux will follow, right? Likewise, you can take a copper wire, as I give you the example. When you are keeping the switch on, then the copper wire, because of its high conductivity or low resistance, confines the current within itself. So when you switch on the power, the current is flowing through the wire and it reaches to the appliances, either light or fan. Right. Similarly, you can use a ferromagnetic material. The example for steel, transformer steel also, which is due to its high permeability, allows the flux to pass through it. It offers very low resistance to the flux, so it confines the flux to it. But unlike the electric field lines, the lines of magnetic field forms the closed loop. The manner in which current is flowing exactly in the similar manner, the flux is not flowing. Right. The current is passing through a conductor. That is a movement of electrons. But flux is established in the circuit. Flux is not moving in the manner in which the current is moving through electrons. Right. So flux, you can tell, established in the circuit. Then there is a source which will produce the energy, which will produce or establish the flux. So that is known as MMF, magneto-motive force. Current in the circuit is flowing due to motive force. Potential difference, as we discussed last time. The current is flowing in the circuit. In the similar analogy, in a magnetic circuit, the magnetic flux is due to existence of MMF, magneto-motive force. This MMF is produced by ampere turns, by current flowing through a coil. So actually there are two types of magnets, natural magnet and electromagnet. So we're talking, if we talk about electromagnet in magnetic circuit, then the value of MMF produced by it is proportional to the product of current and number of. So the unit is ampere turns, AT, right? So generally turns does not have any units. For dimensional analysis, it is amperes, right? So this is about MMF. Any doubt here, anyone? So MMF is magneto-motive force. Comes magnetic field strength, that is H. You can tell it is ampere turn per meter, MMF per meter length. So magnetic field strength is defined as MMF per meter length. And there are various labels associated with it: magnetic field strength, magnetic field intensity, or force. Right. So all these are name given to the magnetic field strength. That is, capital H is the symbol, and the unit, as you know, is AT per meter. So this H is F. F is MF, unit of MMF, and this is the symbol of IN. So that is IN is ampere turn, and this is divided by L is per meter length. So the value of this H is AT per L. Clear? So if you look to the magnetic circuit shown here, then look at the circuit. This is the coil. It is wound around a magnetic. This is your magnetic material. Right, and this is the coil which is wound. Current I is passing through the coil. And due to that, N is number of turns of the coil. So N into I is the MMF produced by this coil, and that MMF causes the flux phi to flow through. Flux phi is established in this magnetic material, whose area is A meter per square. So if you consider the unit length, circumference, that is L. So this is that length L. Then H is defined as Ni upon L. Clear? Any doubt here, anyone? Then you can ask. Always feel free to ask in case of any query. These concepts you already learned during your 11th-12th standard, but this is the basic of your. So I'm discussing it here. Still, if you have any doubt, you feel free to ask. Right, I am sharing my screen again. So this is magnetic field strength. Then comes permeability, mu. So there are three terms you can tell. One is conductivity, right? One is permeability, another is permittivity. So permeability is the ability of magnetic material to establish the magnetic flux in the magnetic circuit. And it is with the relation with flux density B, right? B is the flux density phi upon A. So the relation between the flux density and magnetic field intensity is established by the permeability mu, right? So this is the symbol where mu0 is the permeability of air, right? So if you consider the permeability of air or vacuum as mu0, it is 4 pi into 10 raised to minus 7 is the permeability of vacuum or air. Clear? And the relation is B equal to mu H. So that B equals to mu H if the media is other than the vacuum or air. And for that you can take mu equal to mu0, that is permeability of vacuum or air, and into R, the relative permeability of the medium you are referring. Clear? So the flux produced by the given MMF is greatly increased if iron is replaced by the air in the core. If you use iron, so its permeability is high compared to air. So the B will increase. So as I have written in the previous slide, this is the equation for B equal to mu H, right? Mu is the permeability and relation is mu equal to mu0 into mu R. Mu R is a relative permeability, is the ratio of mu upon mu0. So it's a number without any unit. Then reluctance and permeance. Reluctance in some literature it is referred as S also. Here it is referred as R. So reluctance is actually the opposition offered to the flow of flux. So the current in electric circuit is opposed or limited by the resistance. In the similar manner, the flux phi in a magnetic circuit is controlled or limited by the presence of reluctance. That is, as opposition offered to the flow of flux is reluctance. So if you take the equation, the dimensional equation of resistance, then you can tell R equal to rho L over A, right? Where rho is resistivity, L is the length, and A. Similarly here reluctance S or R is 1 upon mu L by A, right? So where mu is permeability, which is given by mu0 into mu R, right? And opposition of the reluctance is known as permeance, right? That is G. Another equation of resistance, if you recall, R equals to, as per Ohm's law, V upon I, right? Similarly, the equation of reluctance, S, will be MMF upon the flux, is the voltage upon flux. So it is Ni is MMF upon the flux phi. Clear? Any query here? Then you can ask. Always feel free to ask. Huh? Never hesitate.
લોબીમાં કોઈ છે?
Imagine it is advisable to join the class within first 5 or 10 minutes because I am sharing the screen. પછી શું થાય કે I have to come back here again in this screen to admit. It creates disturbance to learning, right? So it is always advisable to join the class within first 5 to 10 minutes. I am sharing the screen again. So if you take generalized circuit theory, magnetic circuit relations, then you know MMF is ampere turn. Because of this MMF, right, the flux is established in the circuit and you have the magnetic field strength set up throughout the length of the circuit, that is L. So you can tell H is MMF upon L. So MMF is H into L, right? If B is a flux density, then you know the flux density equation B equal to flux per area. So it is phi upon A, area of the magnetic circuit, right? So using that equation, you can tell flux is B into A, right? So if we move with this equation, phi upon F, right? Recall this, we are doing phi upon F. Of phi and F in the next slide over here. So it is this BA upon H into L. We are separating B by H, A by L, right? So if B by H is mu, right? Because B equal to, we already seen that B equal to mu H, right? So B by H, you can put value of mu. So that mu is put here. So mu upon AL, mu is your mu 0 into mu R. So putting the value of mu here, mu 0 into mu R, A by L, right? So phi is what? F upon F will go on the numerator. So F upon that is MMF. Remember this F is your MMF upon this L by mu 0 mu R A. So this is similar to what I have written comparing with your standard equation. This is R or reluctance. So you can tell that the flux is MMF, right, upon the reluctance. So similar equation we have derived here also. Clear. So now after discussing the basic, in next slide we'll discuss the analogy. That is the comparison between and the magnetic circuit. So by the term analogy means similarity or comparison. So in electrical circuit, if you are referring to the EMF, whose unit is volts, here it is mmf, unit is ampere turn, like current for flux, reluctance for resistance, conductivity for this, right? So likewise, you can find many this analogy or similarity in equations and all of the stuff. But can anybody tell what is the difference between this? Electrical circuit and magnetic circuit. There are few differences. The first difference I have already explained. The electric current is actually flowing in the circuit. The magnetic flux does not flow the sense in which electric current is flowing. Right? Jerry, the electric current is flowing. In the same manner, the magnetic flux will not flow. The flux is established in the circuit. Right? This is the first difference. Second difference, the magnitude of resistance and reluctance. So the magnitude of resistance does not depend upon the magnitude of current flowing in the circuit. It's a R does not depend upon the magnitude of current. While here reluctance S depends upon the flux density or the flux which is flowing in the circuit. Right. Another difference I would like to tell that in electrical circuit have some good insulators. Good conductors are there, good insulators are there. That means it is possible to insulate the electrical conductors so that you can confine the current to the prescribed path. But mark my words, there are no such perfect magnetic insulator available. The material can be either good conductor of magnetic field or it can be a bad conductor of magnetic field. Magnetic insulator is not available till date. Right. Wood and other materials which are bad magnetic conductors, but it doesn't mean they insulate the flux. Right. We're supposed to join with your number and then name, underscore name. Majority of students have done the same, but few students have joined without the number. I'm sharing my screen again. So now BH curve. B is the magnetic flux density, right? Phi by A. H is magnetizing field strength. So BH curve, these are the, we'll describe BH curve in next session in detail, but just to give an idea, when you change H, how can you change H? Tell me. H is Ni upon L. Right, ampere turn upon length. So once the circuit is designed, suppose તમે circuit you made already, which is visible right now to on your screen. આવી circuit બનાવી નાખી છે. Then N is fixed, L પણ fixed થઈ ગયો because the length and number of turns is fixed now. Right. So you cannot change that. So when you can change the current which is flow turns. So here by varying H means you are changing the current I. And if you look to the B, then B is phi upon A. Again, this design area is constant. So it is the actually flux which is changing. So HB relation means I versus flux relation. So when you increase the current, obviously the flux produced, flux established in the circuit will increase. So initially, for the first time, after manufacture, when you are testing, If the current is zero, there is no flux in electromagnet. So the flux is zero. Then slowly, when you increase current instead, find increase in the current increase in the flux, almost linear. So this linear characteristic you will find for initial regions. That means તમે જેટલા સ્ટેપ્સમાં કરંટ વધારો છો, in the same steps your flux will increase. So that relationship is almost a linear. After that relation, you have a knee portion somewhat pending, which is not that much linear. That means to increase flux, you have to give some more current, right? So that is a knee portion. And after knee portion, the saturation region will come. What is saturation region? Okay, in this region, even if you increase the current, look, you're increasing current so much, but there is a very small or almost negligible increase in B. So this is saturation region, right? Yes, any query going in?
No, sir.
Saturation, if I would like to explain, in other words, so suppose tomorrow lecture start થાય, the lecture duration is generally 1 hour. So someone is start teaching, so dhire dhire tamne ke you are aligned and you are getting something, right? So that is, you can tell, linear relationship. થોડું તમને સમજાવે છે, તને you're getting the points. પછી 20-25 મિનિટ થાય, હાફ એન અવર થાય એટલે થોડો ની પોર્શન આવે. That means સર હજી મહેનત કરી રહ્યા છે, but you are getting a bit less because now you are not able to keep up the attention. Whether it's a physical class or online class, right? So that is obvious. પછી શું થાય કે 40-45-50 મિનિટ પછી સર કે ના, I will increase, ભલે 1 કલાક પૂરું થઈ ગયું, I will continue with my lecture. The sir will continue teaching you for 2 hours, 3 hours. So શું થાય? The saturation state of mind will come. The same subject, same professor will keep on you teaching for 2-3 hours more or more. The sir ભલે મહેનત કરે, but you are not getting anything, right? Sir is putting so much current, so much efforts, but you are not getting that much output, very little increase. So that is your saturation, right? So that is BH curve. We'll discuss each part of BH curve. This is a partial BH curve. We'll complete the entire BH curve also. Again, I am sharing my screen. So this is the BH curve. Clear? Now this is a very simple example. Our type of examples you should be able to solve. You need to calculate, you should copy down the data. MMF, which is required to produce the flux of 15 milliweber or 0.015 Weber, right? Across an air gap of 2.5 mm long. So this becomes your L. You should be able to identify the data. This is your phi. To find out MMF, that is Ni. Right, and this is given the area E. But remember, you have to convert to the same units. So this is given in mm, this is given in centimeter. So if you know the equation of MMF is H into L, right? So you need to find out H matter, you need to find out B. So B is phi upon A. So phi is given 0.015 Weber or 15 milliweber divided by area is in centimeter square. So convert that area into meter square, right? And then you are getting the flux in Weber per meter square, right? So that is 0.75 Tesla. Then calculate H B by mu, right? Because air gap is only given. If other material is given, then they are supposed to give their mu r generally. Okay, mu r of iron is this. You need to multiply mu 0 and mu r to find out the mu, right? And then you can use the equation H into L so that you can find out the ampere turn. So the answer is 1492 ampere turn. Clear? So this type of small numericals related to magnetic circuit you should be able to solve. We'll move to the next topic. This is a composite magnetic circuit. If you look to the previous example, the MF required to produce flux across the air gaps. So only circuit consists of only air gap. Here this is a composite, more than one magnetic material, different reluctance. Suppose this is a one portion, first portion, this one L1, right? It is a magnetic material 1. This is your magnetic material 2. So both are having different dimensions, different lengths, different area, even different material. This is material A, this is material B. So accordingly, reluctance 1 is different, reluctance 2 is different. So when you are using composite magnetic circuit, you need to find out total reluctance by adding them. Clear? So in that case, your total flux will be total MMF. If you look to the MMF, the source is 1. Right, it is establishing the flux through these two parts of the magnetic circuit. So that MMF upon total reluctance. Total reluctance is addition of both S1 and S2 both. Clear? So this is part A reluctance, this is part B reluctance. So this is composite magnetic circuit case 1. We will see another case where you have two reluctances, two different circuits, 1 and 2. Right, their area is same. That's why even A2 is not taken. So area is same. Only L2, whose length is L2, it is an air gap. Right, this is an air gap. This is a classical example where we use all the machines. All electrical machines are like this only. Magnetic circuit, and in between you have an air gap. And this is complete circuit, right? So you can find out the flux also. And this is steps to solve the problem on magnetic circuits, right? Either you can, if you have the value of flux, if you need to find out, you can find out using this way or this way. Then flux density is available. Then you can go for this value or this value. Magnetic field strength, MMF. So all these are interrelations. This you must know all equations. Clear? Do you have any doubt? Any questions in today's session?
No, sir.
Solenoid var
Sir.
Yes.
sir, solenoid વાળો કેસ રિપીટ કરો ને
સોલેનોઇડ એટલે
સર આ જે
composite.
સોલેનોઇડ નું જે આપણે બતાવી એનો જે કેસ નંબર 2 છે રિપીટ કરો.
Okay. Okay, I will repeat the same. I'm sharing my screen again. So this is actually both are composite magnetic circuits. If you look to this, I'm going back. Then this is, you can tell, simple magnetic circuit. Why simple? Because it's one type of material, only one magnetic material, right? But now we will move to the composite magnetic circuit, which is having more than one type of magnetic material, material 1 or A or material 2 or B. This case, पहला case में आपने जो है, both materials are having different lengths. L1 is different, L2 is different. Material is also different, like mu पण बदलाई है, right? Here you can tell mu1 is mu0 into mu A થઈ જાય, the permeability of material A. While mu2 if you take, so it is mu0 into mu B થઈ જાય, right? Relative permeability of material B. So that way, and A is also different, area પણ different છે, it is clearly visible from the diagram. આનો cross section area is bigger A2, this cross sectional area is less A1. So accordingly you can do. Now તમારો જે query હતી, this case in which the throughout the circuit is of the same material. આ એક જ પ્રકારનું મટીરિયલ છે જેની લેન્થ, જેનો એરિયા છે A1. So its permeability mu1 is mu0 into mu r of this material 1. Clear? But second part is an air gap. So it is having a different length, but area is same. So બંનેમાં area same લીધો છે. And here there is no mu r. Why? Because for air or vacuum, mu r is always 1. You need to consider mu0 only. So here only it is mu0. And this is a mathematical treatment. What they've done here is they've taken this 0 and A common. So this will be, if you look to this equation, mu1 upon mu0 will come here and plus L2. So this way you can solve mathematically. એટલા માટે steps આપ્યા છે. બાકી the concept is same. And this is used for all the machines. Crossover be like this only. You have motor, generator, all machines are like this only. Clear?
Yes, sir.
Good.
Yes.
Any other query?